let's consider a harder initial value problem. Oops. Suppose somebody gives you this problem, y double prime plus 3y prime plus 2y equals 0. You could plug in actually in higher order differential equations, find out that the general solution is, you're not expected to derive it in this class, but it turns out that the general solution, the form of all solutions, is y equals c1 e to the minus t plus c2 e to the minus 2t. That's an infinite number of solutions. This comes out that in order to solve a second order equation, you have to do two integrations. It gives you two arbitrary integration constants. And, like the last problem, we got one arbitrary integration constant, so we needed one initial value. This one will integrate twice, get two arbitrary constants, so we'll need two initial values. So two initial values for a second order equation. Suppose I said that in addition to this, I'm given initial values y of 0 equals 2, and y prime of 0 equals minus 3. What is the unique solution to this second order equation with two initial values? Well, we just plug them both in, right? The first one says when t equals 0, y equals 2, and so we put 2 in for y, times c1 e to the 0 plus c2 e to the 0, says that c1 plus c2 equals 2. Then we need to calculate y prime. Let's do it over here on the side. Y prime, the derivative e to the minus t is minus e to the minus t, so y prime is minus c1 e to the minus t. Derivative e to the minus 2t is minus 2 e to the minus 2t. So this is minus 2 c2 e to the minus 2t. There's the derivative. And the second initial condition says that when t equals 0, y prime is minus 3. So we put that into the derivative equation and get minus 3 equals c1 e to the 0 minus 2 c2 e to the 0, or more succinctly, I guess, c1 minus 2 c2 equals negative 3. How about that? Now what this does is it gives us two linear equations for two unknowns, c1 and c2, and we can solve these and we'll get a unique solution. So a second order equation gets two initial values, one for y and one for y prime at the same value of t. And here's the system of equations. How can we solve that? Well, a nice way is to write them in this form. c1 plus c2 equals 2. Put the like numbers, c1 and c2, over each other. c1 minus 2 c2 equals negative 3. Call that equation 1 and equation 2. And we could add a multiple of one equation to another, right? Suppose we take the first one minus the second one to eliminate c2. So if I take 1 minus 2, what do I get? c1 minus c1 is 0. c1 minus a minus 2c2 is 3c2. Equals this one minus this one is 2 plus 3 is 5. Tells you that c2 equals 5/3. Evidently there's a unique solution. Oops. We have to this that y equals c1. Oh, I didn't finish finding c1. Now you can plug 5/3 into either equation to get c1. If c2 is 5/3 and c1 plus c2 equals 2, that tells you that c1 is 1/3. 5/3 plus 1/3 is 2. Alright, so now I deduce, putting these in, that y equals c1, 1/3 e to the minus t, plus c2, 5/3 e to the minus 2t. There's the unique initial value problem solution. Try try section 8.1 homeworks that I'm sending in the email here and see if you can do all these problems now. In addition to this, I want to start 8.2 this lecture. And in 8.2, we consider a particular type of equation that comes up quite a lot called a separable equation. A separable equation, here they'll use x for the independent variable, so y is a function of x. dy dx equals a function of x and function of y. If it can be written in this form, a function of y alone times dy dx equals a function of x alone, then we say the equation is separable, because if we just multiply both sides by dx and integrate like we did on that other problem, we have m of x dx, only x and dx on the left, and n of y dy, only y and dy on the left. We can integrate both sides. Integral n of y dy dx equals integral m of x dx. And this, by the substitution theorem, dy dx is dy. Here it's written as the u substitution theorem. U equals y of x. Integral n of u du equals integral m of x dx. And by integrating, we then get all the solutions to the differential equation. Let's try it on this one here, whose solution I'll put out. Oops. Suppose I wanted to solve dy dx equals 6y squared x, together with an initial value, otherwise I'll get an infinite number of solutions. Y when x equals 1 is 1/25. Alright? So what do? I separate variables. I'll divide by y squared and I'll multiply by dx. So I get y to the minus 2 dy equals 6x dx. Now I integrate both sides, because dy can be written as dy dx and then use substitution. So this is integral y to the minus 2 dy equals integral 6x dx. Integral y to the minus 2 is minus y to the minus 1. Integral 6x is 3x squared plus a constant from the integrations. Gives us, this is the general solution set. I just have to solve for y. And what I'll do is, before I do that, I'll plug in the initial value. I'll plug in that y equals 1/25 when x, y is equal to 25, 1/25 when x equals 1. And that determines that c is equal to minus 28. Consequently, I can put that in the equation, get minus 1 over y is 3x squared minus 28. So there's how the initial value determines the integration constant. Now I solve for y and get y equals 1 over 28 minus 3x squared. There's how to solve an initial value problem when it's a first order separable equation. You simply separate the y with dy on one side, x with dx on the other side, slap an integration sign on each side that's equivalent to a u substitution. Plug in the initial value after integrating, and you get the unique solution, generally unique solution to your initial value problem. Here's another problem. Suppose I have y prime equals this quotient. What a mess. Well, I can still separate variables. I multiply by 2y plus 2y minus 4 and multiply across by dx, and I get 2y minus 4 dy equals 3x squared plus 4x minus 4 dx. X's and y's are separated each side, so I can slap an integral sign on there. When I integrate this side, I get y squared minus 4y plus an arbitrary constant. I'll put them both on this side. Integrate this side, I get x cubed plus 2x squared minus 4x plus c. Now, I also have the initial value, y of 1 equals 3, so I can plug in that when x equals 1, y equals 3 in this equation, so I plug in 3 for y in each of the spots and 1 for x in each of the spots. That determines that c has to be negative 2. I infer that my solutions are y squared minus 4y equals x cubed plus 2x squared plus minus 4x minus 2. Well, this is technically not a a solution to the differential equation, right? A solution is y a function of x that satisfies the equation at each point. So I have to solve this for y. Well, I can use the quadratic formula. I'll put this over on the left and think of this as ay squared plus by plus c equals 0. If I apply the quadratic formula, minus b plus or minus square root b squared minus 4ac all over 2a, I get this solution. Now I've got a solution for y as a function of x. Oh, there's a plus or minus. Why is that there? Well, what happens is it turns out that both of these are solutions. You can put the plus sign in or the minus sign in, and you get a solution, y as a function of x. Alright, we'll try the problems on separable equations, and send me any questions you have.